from our last video, we spoke about the motion of a charged particle in a uniform electric field. So we have this problem um, to actually test our knowledge of what we learned in the last class. So here we have an electron. We said an electron enters the region of an electric field shown above with this initial velocity here, and this is the electric field in this region. The electric field is 200 Newton per coulomb. The horizontal length of the plate is given to be 10 centimeter, so the length of the plate is 10 centimeter. So the problem here is to find, first of all, we are asked to find the magnitude of the acceleration of the electron. Number two is to find the time taken for the electron to move out, to leave. When it starts from here, how long will it take to leave? And finally, what is the vertical position, meaning the vertical displacement of that electron? So from the last video, we understand that when this electron enters into this field, when this charged particle enters into this field, there should be a force that will act on it. There should be an electric force that will act on it because of the electric field in this region here. So we understand the fact that our electric field should equal to the electric force acting at a point, on a point charge, on a test charge, per the value of that test charge. So our electron is acting as our test charge here. So the field in this region, the uniform field in this region here, should equal to the force that will act on any charge that enters into that region. So that means electric field is force over this, and of course, this will eventually give us that the force is QE. So we have established this already, and we understand that that force is only acting along the vertical. So we have also established this from the last class, and we know that this force is equivalent from our Newton's second law is also equal to ma. So we know that to find the acceleration of this charged particle here, I just need to equate these two equations. We already have the equation, but I'm just trying to derive it again. So from here, that means our ma should just equal to QE. But it is important to note that this force, which is a vertical force, will also give us a vertical acceleration. And that is why this electron, when it enters into this field, it will be accelerated towards the positive plate. It's a negative charge, it will be accelerated towards the positive plate. So that force that will accelerate it is a vertical force, Fy, only along the vertical. That means the acceleration should also be along the vertical. So the acceleration is only along the vertical, there is no acceleration along the horizontal. So it is that acceleration we are looking for, of course, the magnitude. So that means I'm not interested in the sign of our charge, I'm only interested in the magnitude of the charge. So the acceleration is just QE upon m. Just make this guy subject of the formula. So what is our Q? Q is the charge that enters into the field, which is the electron. The magnitude of an electron is just 1.6 by 10 raised to power minus 19 coulomb. And what is our m? M is the mass of an electron, which is approximately 9.11 times 10 raised to power minus 31 kilogram. And E is the electric field. We have been given the field in that region to be 200 Newton per coulomb. In some problems, we might not be given the electric field. We can be provided with a potential difference between the plates. We can be told that if the two plates are connected to a potential of, let's say, a potential of 100 volts, and we know the distance between the two plates, there's a connection between electric field and potential difference. The electric field, of course, magnitude of electric field is the potential difference over the distance between the two plates. So I can use this to also determine our E. But in this problem, we are given the E directly, so I'll just apply directly. So that means the magnitude of the acceleration is just QE, which is 1.6 times 10 raised to the power minus 19 times our E is 200 divided by the mass. This guy minus 31, and I will have my acceleration. So if you punch your calculator, the acceleration should come out to be 3.51 times 10 raised to the power 13. 3.51 times 10 raised to the power 13 meter per second square. So that is the acceleration of the body in this uniform field. That's the acceleration that we are going to get. Very easy and straightforward. That's problem A. To problem B, we are asked to find, they say if the electron enters the field at time t equal to 0, at which time, okay, find the time at which it will leave the field. Meaning, what is the time taken for it to move from this point, the beginning of the field, to the end? What is the time taken? And from our last video, we were able to derive the time. We said the time taken should just be obtained from the distance covered, the horizontal displacement upon the initial velocity. Where is this guy from? Of course, from the fact that the horizontal displacement should equal to the initial horizontal displacement times time plus half ax t square from your normal equation of motion. And since we know that the acceleration is only along the vertical, ax is 0, this part is out, so sx is equal to what? V naught x. What is this our sx? The horizontal distance L traveled. What is this V naught x? This is the initial velocity horizontally. The body, the electron is projected horizontally. It is moving horizontally into the field. That means that the initial velocity horizontally should be the entire, because this is VII. This is indicating that, oh, the electron is being projected horizontally. That means that the initial velocity is only along the horizontal. There is no vertical component for the initial velocity. That implies that our V naught of x is simply VI. It's simply VI. So this is VI here. So that means this is VI here, and this is the time t. So if you make t subject, you are going to get this formula, L over VI. So the time taken for that electron to travel from here to this point here is just the length of the plate upon the initial velocity VI. And what is that here? What's the length of the plate? The length of the plate is given, the length is 10 centimeter. You do your conversions to meter, divide by 100, that's 0.1 meter. And the initial velocity VI is given to be 3.0 times 10 to the power of 6. So if I divide that, so this is just to show this formula again. If I divide, that means our t should give us 0.1 divided by 3.0 times 10 to the power of 6. And what will that give you at the end of the day? You punch your calculator again. This should give us 3.33 times 10 to the power of minus 8. 3.33 times 10 to the power of minus 8 seconds. So this is the time taken. Of course, I can also write this as 33.3 nanoseconds. Nano is 10 to the power of minus 9. So if I move it forward, I can subtract 1, and minus 9 is nano. So this is correct. This is equally correct. So that is for question B. Finally, question C, we are asked to find, if the vertical position of the electron as it enters the field is y naught, meaning that it is entering, this particular point here is described to be the origin. So I can continue like this and assume that this is the origin here. So that means that if you look at the motion of this charged particle, it moves like this. That means that there is a vertical displacement here. So that is the question. The question is to find the vertical position as it leaves. So while it is leaving, there is a vertical displacement here, which I can call our y. I'm only interested in the magnitude of that displacement. And from our last video, we were able to get that formula as well. And what is that guy? So people that, if you have not seen that video, let's see it together. From sy equal to v naught yt plus half ayt square. From this our formula here, what is v naught y? There is no initial velocity vertically. The body is projected horizontally. That means v naught y is equal to 0. And we know that our ay from our formula there is QE upon M. And our T is what? We have gotten our T already to be that value, which is simply L over VI. So, and we have gotten the value to be 3.33 times 10 raised by 8. If I slot everything back here, where my SY is the vertical displacement Y. So if I use my SY as Y and slot everything back, from our formula, I've given the formula before, we are going to get half QE upon M times T square. What's our T? L over VI all square. So this is formula for our Y. I'll just insert my values and get my result. 1 over 2 times Q, 1.6 times 10 raised by minus 19, that's our Q. The electric field E, which is 200 upon the mass, which is 9.11 times 10 raised to power minus 31. In fact, all of this is our acceleration that we have gotten before, but I'm just solving it again so that you will see. Times, and we have gotten this as our time before, but let's insert the values again, which is 0.1 upon 3.0 times 10 raised to power 6 all square. If you punch all this or use the value of acceleration and the value of your time, you will get the solution for your y. So if you punch your calculator, your y should come out to be what's that value? If you punch it properly, your y should come out to be 1.95 times 10 raised to power minus 2. 1.95 times 10 raised to power minus 2 meter, which is basically 1.95 centimeter. So that is how you solve problems like this. You are expected to just use your knowledge of projectile motion and understand that you have to break down the motion of this object to the vertical and the horizontal motion, and that's all. Thank you.